Let me ask you a question. Are time and distance even real? I mean, really real. At least not in the way you probably think they are. In this explainer, we're going to dive into these fundamental concepts, and we'll be using the revolutionary ideas of the one and only Richard Feynman as our guide. So, what on earth does Feynman mean by how long we wait? Well, he's getting at something absolutely crucial about physics. You see, it's not about abstract philosophy or dictionary definitions. For a physicist, a concept is only useful if you can measure it. The definition of time isn't a sentence, it's the actual clock you built to track it. So if it's all about measurement, where do you even begin? Well, you start at the beginning. Long before we had laser precision and atomic clocks, people had to get creative. They used the most fundamental tools they had, their own bodies. And that's exactly what a guy named Galileo did. Now, what's so cool about this is just how simple it is. Galileo wanted to study motion, right? But he didn't have a stopwatch. So what was his solution? He used his own pulse. As a ball rolled down a ramp, he'd mark where it was at each beat of his heart. 1 beat, 2 beats, 3 beats. It was this incredible act of turning a biological rhythm into a scientific instrument. And what he found was a complete game changer. The distance the ball traveled, it wasn't random. It followed a beautiful, predictable pattern. What you see here, d is proportional to t squared, was that pattern. Now, proportional to just means that as one thing changes, the other changes right along with it in a set way. And time squared, that's just time multiplied by itself. So after 2 heartbeats, the ball had gone 4 times as far. After 3 heartbeats, 9 times as far. This wasn't just some casual observation. This was a mathematical law of nature, one of the first ones we ever figured out. Okay, so Galileo's pulse worked great for a rolling ball. But our curiosity didn't stop there. We looked up to the stars. How in the world do you measure something you can't possibly reach out and touch with a ruler? We had to get clever. To measure the distance to the moon, for instance, we used something called triangulation. You can actually try this right now. Hold your thumb out, close one eye, and look at where your thumb is. Now switch eyes. See how it jumps? Well, knowing the distance between your eyes and that little jump, you can calculate how far away your thumb is. Astronomers did the same thing, just with 2 different points on Earth. And for something like Venus, we could do something even cooler. We literally fire a radar beam at it and just time how long the echo takes to come back. Totally different methods, but they give us the same answer. And what about measuring really, really long stretches of time, like the age of the Earth? We can't count the days on that one. So instead, we use nature's own long-running clock, radioactivity. You see, elements like uranium-238 decay at this incredibly steady, predictable rate. It's called their half-life. So by measuring how much is decayed inside ancient rocks, we can calculate their age in billions of years. All right, we've gone big, we've looked out to the stars. Now let's go in the complete opposite direction. Let's shrink our perspective way, way down, past anything the human eye can see, and journey into the impossibly small world of the atom. So how do you measure something you can't possibly see? You have to be indirect about it. One trick is to shoot X-rays at a crystal. The X-rays bounce off the atoms inside, which are all lined up in a neat little pattern, and that creates a pattern of its own. By analyzing that pattern, we can figure out the distance between the atoms, which is about a 10 billionth of a meter. And the nucleus at the very center of that atom? It's 100,000 times smaller than that. The scale is just mind-boggling. And this image right here, it just perfectly shows the scale we're talking about. See that big white sphere? That's just there for scale. It's only 200 nanometers across. The little things are viruses, and every single one of those is made of millions and millions of atoms. We're really talking about the fundamental building blocks of matter here. But at this tiny, tiny scale, we run into a wall. A fundamental wall built into the fabric of reality itself. It's called the Heisenberg uncertainty principle. Now, the formula might look a little scary, but the idea behind it is profound. This little triangle, delta, just means uncertainty. So delta x is our uncertainty about a particle's position, where it is. And delta p is our uncertainty about its momentum, basically where it's going. What the whole thing means is you can never ever know both of those things perfectly at the same time. The more you know about where it is, the less you know about where it's going, and vice versa. The universe just has a built-in level of fuzziness. So we've seen how we measure the incredibly big and the incredibly small. But the biggest revolution in our understanding of time and distance came when we realized our rulers and our clocks, well, they aren't as solid as they seem. So here's the crucial point. Before Einstein, pretty much everyone just assumed there was one master clock for the whole universe, just ticking away the same seconds for everyone, everywhere. But Einstein's theory of relativity completely shattered that idea. It says that measurements of time and distance are relative. They literally depend on how you're moving. Now, to get your head around this, and it is a bit of a mind bender, Feynman used this brilliant thought experiment. He called it a light clock. Just imagine two mirrors with a little pulse of light bouncing between them. Every time the light hits a mirror, that's one tick of our clock. Super simple, right? Now, for the big question, what happens if this clock starts moving? Well, if you're standing still watching that clock whiz by, the light doesn't just look like it's going up and down anymore. It has to travel a longer diagonal path to catch up with the moving mirrors. And here's the kicker. The speed of light is constant for everyone, no matter how they're moving. So, if the light has to travel a longer distance, but its speed can't change, there's only one possible conclusion. Each tick has to take longer. The moving clock runs slow. This leads to a truly profound insight. Feynman uses another analogy. Think about a box. Its width and its depth kind of depend on how you're looking at it, right? If you walk around to the side, what you called width now looks like depth. They aren't fixed properties, they're just aspects of your perspective. Feynman wondered, what if space and time are the same way? What if my measurement of 1 second and your measurement of 1 meter are just different slices of a single deeper reality? And that's where we get this incredible concept of space-time. It's not 3 dimensions of space plus time as a separate thing. No, it's a single 4-dimensional fabric. When you snap your fingers, that event doesn't just happen at a place. It happens at a place and a time. It's a coordinate in space-time, just as real and solid as a point on a map. So on a space-time diagram like this one, a particle that exists over a period of time isn't just a point. It's a line, its entire history, its world line, stretched out through space-time. If that particle decays into 2 other particles, the line just forks. This isn't just a picture of motion, it's a picture of existence itself. So, if everyone's ruler is different and everyone's clock is different, is anything constant? Is anything the same for everybody? Amazingly, yes. There's this one special calculation you can do called the space-time interval. It combines the time that passes and the distance and space between 2 events in this very specific way. And even if my clock says 5 seconds passed and your clock says 7, when we both do this calculation, we will get the exact same number. This is the true absolute distance between 2 events in 4-dimensional spacetime. It's the one thing we can all agree on. And that brings us full circle, right back to Feynman's core idea. We started this whole journey by trying to define time and distance, only to discover that our definitions completely depend on how we measure them. From Galileo's pulse all the way to the fabric of spacetime, we've learned that reality is absolutely not what it seems. Our most basic, common-sense intuitions about the world are just shadows of a deeper, 4-dimensional reality. And maybe the ultimate lesson from Feynman is this: don't trust your assumptions. The universe is far stranger and way more beautiful than our everyday experience lets on. And the only way to really see it is to measure it.